1, 2, 3, 4, 5, 6, 7.
Numbers go on and on and on forever.
I think we all remember asking mom or dad as a child what the biggest number was.
And it probably went just a little bit like this.
Dad, what's the biggest number? Is it 100, 1,000, maybe even 1,000,000?
Son, I hate to break it to you, but there is no such biggest number. The beauty of math is that numbers go on forever.
Forever?
Yes, and we represent this by the sign of infinity, a horizontal 8. And it is truly astonishing that these simple, never-ending numbers dictate our understanding of modern math, and by extension, our understanding of the entire universe. A universe in which we have found to contain numerous infinities within itself.
But what is infinity?
Well, that's a difficult question. Infinity is a concept that not only our mathematical systems struggle to define, but seemingly even our universe itself.
All right, well, how are infinities relevant to our universe? A prime example of the scope of these infinities within our own universe are the dark voids themselves, black holes.
And according to Einstein's theory of relativity, the density of a black hole is infinite at its singularity, that being its center.
This infinite density makes it so that whenever something enters a black hole, it will only be moving closer to the singularity, regardless of if it's pointed away. In our world's understanding, for example, if an astronaut were moving in the opposite direction of the spaceship, he'd obviously be getting further away.
In contrast, if that spaceship just so happened to be the singularity of a black hole, then no matter what path he takes, that astronaut would always be moving closer towards the center.
The singularity is always ahead of you. It's always in your future, regardless of what path you take. So this is where understanding of physics begins to break down, as direction loses meaning, since any path you take just leads you back to the same point.
And I'd also like to add that black holes pull the fabric of space and time along with them. This means that a day near some black holes could be decades here on Earth, and time becomes barely comprehensible.
All right, let's try something more comprehensible. Picture this, you have a lamp, and you have 2 minutes to flick the lamp on and off as much as you'd like.
Let's say the lamp starts off. But what if, after every half of the time remaining in the current interval, you'd flick it on? So after the first minute of the 2, we'd flick the light switch on. And then 30 seconds later, it'll go back off. 15 seconds after that, it's back on. And 7.5 seconds afterwards, it's back off. So on and so forth.
We'd be having each subsequent interval. The time would approach those 2 minutes, but it'd never truly reach that 2-minute mark, as we're only ever inching forward in fractions. So there'd always be a next step. There'd be an infinite amount of steps, all within this finite set of time, those 2 minutes.
But now think, once those 2 minutes elapse, as time inevitably does, will the lamp be on or off? This is known as Thompson's lamp, a famous super task, an infinite task.
The answer to this paradoxical question?
We just don't know.
The lamp can't end in an on state because whenever the lamp is flicked on, it's always followed by being flicked off. And it can't end in an off state because whenever the lamp is flicked off, it's always followed by being flicked on. So there's always a next step. We really just don't know.
But if somebody does have a better idea, please do let us know.
How about we try another one?
Sure. Maybe something a little more delicious?
Sure. What if we had a cake, a delectable cake, as cakes are?
Well, in that case, we can agree that the volume of this cake is finite. There's a finite amount of cake on this table. But how about this? What if we cut the cake in half?
Notice that when we cut the cake in half, the volume, how much cake is on this table, stays the exact same. But what does change is the surface area. Before we had cut the cake, the surface area was on the outside and the top. But after we've cut the cake, the surface area has increased to include not only the outside and the top, but the inside of the cake as well.
So now, if Ammar cuts it again, it's the same thing. The volume remains finite. There is the same amount of cake on the table. However, the surface area is ever increasing.
Let's keep doing this again and again and again. Let's do it forever. Let's do it an infinite amount of times.
And in that case, the surface area continues to increase up to infinity, while the volume, the amount of cake, remains the same.
This is famously known as Gabriel's cake.
And it's important because the surface area, if we wanted to frost this cake with an infinite surface area, we would need an infinite amount of frosting.
So it's a cake you can finish eating, but never finish frosting.
All right, let's put that away. Lastly, a little more technical concept that showcases the breadth of infinities is related to their size.
I know, it sounds ridiculous to discuss the size of infinitely large things, but hear us out. We know we can square numbers. 2 squared is 4, 4 squared is 16, 8 squared is 64, and so on and so forth. Once we're done squaring all of our numbers, we'll end up with an ever-increasing list of numbers that we can consider perfect squares. These are numbers with perfect square roots. For example, 64 would be one of these numbers because it has a perfect square root of 8.
Think times tables. 1 times 1 is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36, 49, and so on. We can agree that the amount of perfect square numbers is less than plentiful, as there are a majority of non-perfect squares in between. For example, the numbers 10, 11, 12, 13, and 14 all happen to be non-perfect squares.
So with this, one would be safe to assume that there are less perfect square numbers than non-perfect square numbers and perfect square numbers combined. Right? I mean, the second list practically contains every positive number in existence.
Well, it actually doesn't work out like that. And this is again because numbers go on to infinity. And with an infinite amount of number, each number can be multiplied by itself to produce a corresponding perfect square. For example, 7 squared is 49, 49 squared is 2401, and 2401 squared is who knows. But the point remains, because each list goes on to infinity, and each item on each list has a one-to-one correspondence in the other, neither list can be greater than the other. For example, for 7, it's 49, for 8, its correspondence is 64, and for 64, its correspondence is 4096.
So then which case is it? Are there less perfect square numbers, or are there the same amount?
Yet again, it just isn't clear. But we're always taking suggestions.
This is famously known as Galileo's paradox. It's exactly as it sounds. It's a paradox that remains unsolved within the world of mathematics. Math is weird, and it definitely gets weirder, but that's what makes it so beautiful.
And while we don't expect any of you to solve some of history's greatest paradoxes today, we do hope that you understand and appreciate that these little numbers dictate everything from the 10 fingers on our hands to the binary foundation of our computers to the vital frameworks of our very existence.
These same numbers that are so fascinating to explore in their infinite uses continue to fascinate in their less paradoxical, and to be quite frank, more practical applications. It's a miracle we even understand a portion of the math that defines our universe, but it's why we've thrived, creating civilizations larger than the moon, to reaching out for it, and breaking the barriers in space that lie ahead of us.
And today, with all of the fundamentals of our universe seemingly described by our letters and numbers almost randomly scribbled down, it's a marvel that these same symbols just so happen to dictate almost everything else about our very existence. And our pursuit for this understanding is crucial to where we've come and where we're going.
So the next time you flick a lamp, try to imagine, understand, and appreciate all the endlessly complex and headache-inducing equations that went into designing such a seemingly simple thing. If any of today's examples have intrigued you, we implore you to look deeper in the universe of mathematics is you'll find a world of numbers other than our own.
And yet, as our systems grow ever complex, it will always be these same numbers we've been counting up from since childhood, dictating their function.
8, 9, 10, 10,033, 100 million.
Humanity won't stop. We can't stop counting.
To infinity and beyond. Thank you.
Thank you.